Today I want to talk a little bit about acids and bases and to go through some of the chemical definitions for them because they're kind of complicated, even though we think about acids and bases and kind of the everyday chemistry kind of applications. We have a lot of acids and bases in our diets, for example. We find a lot of them in our kitchens and our bathrooms. But when we're thinking about them from chemical perspectives, based on the way that they react and the things that we focus on in those reactions, we have a number of different ways that we can define them, even though we're talking about the same thing. It's just all about the reaction context that it's in. So in this video, I want to focus on 3 different chemical ways that we define acids and bases. And I want to start off with the Arrhenius definition, which is kind of always the one that we start off with. So Svante Arrhenius, we see in a lot of different contexts. He's involved in acids and bases. He was the first one who came up with the idea of ionic theory of solutions, where ionic compounds dissolve, they form electrolytes. And that's really kind of how this whole acid-base defining system came about, was dissolving things in water, because the definition for Arrhenius is based on what does the thing do in water? How does it react with water? What happens when we say that an acid dissolves in water? And the key defining feature is when an acid reacts with water, it forms what is called the hydronium ion, or H3O+, and then kind of whatever is left over. So the hydrogen from my acid forms or kind of gloms onto the water molecule, giving me hydronium, and then the other thing that's left over when you get rid of all the hydrogen is the anion from the acid. And of course, anions are the negatively charged things. So kind of the go-to example for these is, hydrochloric acid. So when I have hydrochloric acid with water, then the hydrogen, this thing splits apart. It's an electrolyte, so it splits apart into its component pieces, forms hydronium. There's my key defining feature. And then what's left over is my chloride ion. Okay, so this hydronium then is how I know that I have an acid. Forms hydrogen in solution, and those hydrogen ions like that water molecule. And you'll kind of see why in future videos when we talk about weak acids and strong acids and kind of equilibrium and get into all of that. So hydronium or hydrogen ions in solution are the definition of an acid. A base then, when it reacts with water, forms hydroxide, so OH-, and whatever cation is left over from the base. So what we're saying is that the base dissolves in the water, it splits apart, it dissociates into its component pieces. We'll have a hydroxide that is hanging out, it's aqueous, surrounded by water molecules, and then whatever cation is left over. So if we think about sodium hydroxide, which again is kind of the go-to example for a base, so all first and second group metal cations paired with a hydroxide are strong bases, except for beryllium. And when we react that with water, then we end up with hydroxide and sodium. Now you'll note that I don't have water in my products here, so if I was trying to balance out this reaction, it wouldn't work very well. I could put water on both sides. I could put these guys as aqueous and sort of just say, well, water is the reaction condition. Sometimes you'll see water over the central arrow there that just shows that water's hanging out, that water is allowing this thing to dissociate, so this thing just splits into its component pieces, but the important bit is the hydroxide. Okay, so acids form hydronium, bases form hydroxide. And when we react those two things together, if we react together an acid and a base, then they react together in a neutralization reaction. And these neutralization reactions have that metathesis or double displacement type setup. So if AB is my acid and CD is my base, then I form AD and CB, right? It's that kind of double displacement. We rearrange our partners there. And in a neutralization reaction specifically, if this is my acid and this is my base, then the hydrogen from the acid and the hydroxide from the base form water. that is always going to be a product, right? And that comes from this reaction here, the hydronium and the hydroxide. When you react them together, they want to form water. Water likes to form. And then a salt. And salt in this context could, of course, mean table salt, and I'll show you that reaction here in a second. But it also means just any ionic compound that forms through this type of reaction. So let's take our two examples here and react them together. My acid is my HCl, and my sodium hydroxide is my base. So if we kind of think about these things and break them up into their component formula units here, then I have a hydrogen ion, a chloride ion, the sodium ion, and the hydroxide ion. These guys all split apart. They dissolve. And they dissolve because these two are strong. So it's a strong acid and a strong base. And then they swap partners. So the hydrogen and the hydroxide form water. And the sodium and the chloride, which is quite soluble, will of course stay as sodium and chloride ions, but when we're writing it as a balanced chemical equation, we kind of tend to do it in the molecular formula way, where we show that ionic compound together. If we were doing a net ionic equation, then we would just show that hydrogen and the hydroxide form the water, and that's really the take-home message of neutralization reactions. So that's kind of the defining feature of our Arrhenius definition, is it gives us a way to explain neutralization reactions, to explain how the pH can change as we react to other acids and bases. Okay, so that's definition one. Now the second way we define acids and bases is based on the Bronsted-Lowry definition. So Bronsted and Lowry were two scientists that were working independent of each other and kind of came to the same conclusions. And what they were studying were reactions where we had acids and bases, but it wasn't necessarily how they dissolved in water. So we needed a different way. We needed a broader way of defining them. I think there's a slash through Bronsted there. It's kind of a moon language looking O. Okay, so it's really about transferring a proton. And proton here, we mean a hydrogen ion. So we know that hydrogen is just one proton, one electron, and it's kind of normal, everyday run-of-the-mill hydrogen atoms. When we lose that one electron, we form H+, and when I lose that one electron, all I have is a proton left over. So we can define our acids and bases based on the movement of hydrogen ions or protons in the reaction. So our acid then is our proton donor. So it gives up its proton, which is the same idea as what we saw in the Arrhenius definition, right? So that proton would just glom onto our water, forming hydronium. And then the hydrogen or proton, hydrogen ion or proton acceptor is the base. So in my example that I was just saying, my water then would act as a base because it's accepting that proton from the acid that's donating it. So we have this relationship between the acid that gives up this hydrogen and the base that accepts it. So when I'm thinking about reactions, instead of that neutralization reaction like we saw with the Arrhenius definition, I have to be given an entire setup to kind of figure out what's going on with Bronsted-Lowry, because I need to identify on both my reactants and product side what's happening, what is being lost, what is being gained, how are the hydrogen moving. So I'm always keeping an eye on the hydrogen in my reaction. Where did it go? Who got more? Who got less? Etc. All right, in this one here, if we map out what's going on going from my reactant side to my product side, my HCl is going from HCl to just the chloride ion, right? This is the only thing with chlorine in it. This is the only thing with chlorine in it. So this has to become this, right? So my hydrochloric has to become this chloride ion. So what happens? Well, this hydrogen had to go somewhere, had to be donated to my water. And so my water went from H2O to H3O. So it accepted it. So here's my acid then, my proton donor, my base, my proton acceptor, and then there's a relationship between my reactant side and my product side. My base has a conjugate acid. And if you've ever taken language classes and you've had to conjugate verbs, so if you've studied a language where you have verbs that have to match their subjects, then then you might have conjugated those verbs before. So there's this relationship between them, just like our verbs have a relationship with their subjects. My acid here has a relationship with my base. It's what happens when this base gains a proton. And then my acid has a conjugate base. I also think about it in terms of conjugal visits, right? Like at a prison. So conjugal meaning having a relationship. So what happens going from reactants to products, then there's this relationship between what happens when I lose the proton or donate the proton and what happens when I gain it. So we have an acid with its conjugate base, the base with the conjugate acid. So we call these conjugate pairs. So this is a conjugate pair, my water and my hydronium, my HCl and my chloride conjugate pair. Now if we look at this one, this is a weak acid. And I can tell it's weak because I have this reversible reaction here, which means that the forward reaction is occurring and the reverse reaction is occurring. So we have carbonic acid reacting with the cyanide ion to form cyanic acid and bicarbonate or hydrogen carbonate ion. So if we're mapping out what happens with our hydrogens here, this one's going from 2 hydrogens to 1. This one is going from no hydrogens to 1. So that means that this one must be donating its hydrogen to the cyanide. So this guy is acting like my my acid, whereas my cyanide is acting like my base. It's accepting that proton. And now on the other side, my base has a conjugate acid. So what happens when I gain that proton? And my acid has a conjugate base. So what happens when I lose that proton or donate that proton? Then I end up with my conjugate base or my conjugate pair for that acid. So even without the reaction, I could tell you what the conjugates are for these different things. So if I said, if I have something like HSO4 minus as an ion, and I said, you know, what's the conjugate base of that? Then the conjugate base is going to be what happens when this thing donates a hydrogen. So the conjugate base is going to be the sulfate ion. I could also say, well, what's the conjugate acid of this? And that would be what happens when I gain a proton, right? So if this is acting like a base and I'm looking for a conjugate acid, that would be H2SO4, which is sulfuric acid. Okay, so we say that this substance here is amphoteric, meaning that it can, or amphiprotic, meaning that it can react as either an acid or a base depending on the circumstances that it's in. So it has both a conjugate base and a conjugate acid depending on which way, whether we're donating or accepting a hydrogen. All right, so it's all about protons for Bronsted-Lowry. Now we go to Lewis of Gilbert Lewis dot fame. Same guy. And Gilbert Lewis defined acids and bases based on their electrons, which makes sense because we're, you know, Lewis dot. So acids are electron pair acceptors. And this always makes students mad because an acid is a proton donor, but an electron pair acceptor, kind of tricky. And then the base is an electron pair donor. So we're looking at an entire lone pair of electrons here. So again, this is another one where you kind of need to map it out, and it helps, because it's Lewis, to do Lewis dot structures to kind of see what's going on. So if I take ammonia here, NH3, this is my Lewis dot structure. If I put it in with an acid, then the acid has this proton here, right? There's no electrons here. But when I react these things together, I form the ammonium cation. So we had ammonia, we ended up with ammonium. And how did we do that? Well, this had no electrons to give, right? And this one did. So this lone pair here was shared right here, right? Same lone pair. And this guy just stuck on there. So this one just stuck onto this lone pair. And so when I put these things together, this ammonia here donated this electron pair, and this hydrogen accepted the electron pair. So this is acting like my acid, and this is acting like my base. And this forms one of those coordinate covalent bonds where it's shared. We can do the same thing with BF3 here, our fluoride ion. We have this shared pair here, And then that's the same kind of idea. So this is my donor in that case, which makes it my base.